Good day, everyone. So we are now on our week number 2 for logic design and switching. And for today's lesson, we're going to discuss all about binary logic and logic gates. And for our objective for today, so we're going to describe the logical operators using truth tables. And we're going to recognize the different graphical symbols associated with the logical operators. And we are going to evaluate the output of a simple logic circuit. So what is binary logic? So binary logic deals with variables that take on two discrete values and operations that assume logical meaning. The two values that variables assume may be called different names, but for our purpose, it is convenient to think in terms of bits and assign the values 1 and 0. So there are three basic logical operations. So we have AND, OR, and NOT. So each resulting in one binary value, and we have what we call a truth table. So a truth table is a list inputs of the left and the corresponding output on the right. So it has one row for each possible combination of inputs. And we have also the Boolean equation. So it is a mathematical expression using binary variables. Okay, so let's start with an AND operation. So this operation is represented by a dot or by the absence of an operator. So the output is 1 if and only if both inputs are 1. So below is the truth table of an AND operation with X and Y being the input variable and Z being the output variable. So the number of rows indicates that the number of possible combinations of input and corresponding outputs. Looking at this table, again, we have the input X and Y. Since we have two inputs using the formula 2 raised to n, wherein n is the number of inputs. So in our example, we have two inputs which are X and Y. So 2 raised to 2 is we have 4. So therefore, we have 4 possible combinations. And let us look each possible combination. So let's say we have here X is equal to 0, Y is equal to 0. Therefore, our Z is equal to 0. Let's say we have here the value of X or the input is 0 and Y is equal to 1. Therefore, X and Y is equal to 0. Let's say we have the input X or X is equal to 1. Okay, and Y is equal to 0. Okay, so the value of Z, which is X and Y, is equal to 0. And we have X to be equal to 1 and Y is equal to 1. So X and Y is equal to 1. So we can say that we can only have a value of 1 or Z is equal to 1 if and only if X is equal to 1 and Y is equal to 1. Otherwise, Z is equal to 0. Next is we have the OR operation. So this operation is represented by a plus sign. Okay, so we have a plus sign. And this will be read as X or Y is equal to Z. So the output is 1 if either of the input is 1 or both inputs is 1. So the output is 0 if both inputs are 1. So as long as we have an input of 1, okay, so our output will be equal to 1. So below is the truth table for the OR operation with an X and Y being inputs and Z being output. So let's say we have here X is equal to 0 and Y is equal to 0. So we have X or Y will be equal to 0. Let's say our input for X is 0 and our input for Y is 1. So we have X or Y that will be equal to 1. Let's say we have X is equal to 1 and Y is equal to 0. Therefore, X or Y is equal to 1. Let's say we have X is equal to 1 and the Y is equal to 1. Therefore, our Z, which is X or Y, will be equal to 1. So if you can see from our table, as long as one of our inputs or both of our inputs are 1, so our output will be 1. Otherwise, it is 0. Next is we have the NOT operation, or sometimes we call this one the complement. So, so this operation is represented by a prime or an overhead bar. Okay, so overhead bar. So we should have a bar here. So it negates or complements the input variable so that if the input is 1, the output is 0. And if the input is 0, the output is 1. So below is the truth table of the NOT operation where X is the input and Z is the output. Okay, so if you can see, we have two possible combinations since we only have one input. Again, as we have said a while ago, to get all the possible combinations, we just use the formula 2 raised to n, wherein n is the number of input. Okay, so in our example here, we have one input, so that is 2 raised to 1. So 2 raised to 1 is 2, so we have two possible combinations. So to get the complement of 0, okay, so the complement of 0 is 1. And the complement of 1 is 0. So sometimes we call it X prime. And we have other logic operations. So aside from AND, OR, and NOT, we also have the NAND operation. So AND followed by a NOT operation. So the output is the negation of the AND operation. So it's just the opposite of the AND operation. We have also the NOR operation. So OR followed by a NOT operation. So the output is the negation of the OR operation. We also have the XOR operation, or we call this one the exclusive OR operation. So the output is 1 if and only if either input or not both is 1. And for our XNOR operation, so we also call this one the exclusive OR operation followed by a NOT operation. And the output is the negation of the XOR operation. So let us look the truth table. Okay, so given 4 possible combinations, we have 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so first, let us look for the NAND operation. So this is the NAND operation. So we have here AND, diba? X and Y. So an absence of an operator means that we are using an AND operator. So we have here X and Y, and then we are going to get the complement. So for example, we have here 0 and 0 is 0, and the complement of 0 is 1. So 0 and 1 is 0, and the complement of 0 is 1. we have here 1 and 0 is 0, and the complement of 0 is 1. And we have here 1 and 1, which is equivalent to 1, and the complement of 1 is 0. Okay, so it is the opposite of the AND operation. Okay, so another is we have here the NOR operation. So the opposite or negation of OR operation. So let's say we have here 0 or 0 is 0. The complement of 0 is 1. Next, we have here 0 or 1 is 1, and the complement of 1 is 0. And let's say we have here x is equal to 1 and y is equal to 0. So 1 or 0 is 1, and the complement of 0, or I'm sorry, the complement of 1 is 0. And as for x is equal to 1 and y is equal to 1, so 1 or 1 is 1, and the complement of 1 is 0. So this is the negate, no, of an OR operation. So we call it the NOR. How about XOR? So for XOR, so it says that the output is 1 if and only if either input or not, or both, no, not both, is equal to 1. If you can see, if you have, okay, both inputs are similar. For example, we have x is 0 and y is 0, so both of them are 0. Therefore, our output will be 0. And if our output, okay, one is 0 and the other one is 1, so we have different input. So therefore, our output will be 1. Okay, so same with 1, 0. So 1 x or 0 is equal to 1. And let's say we have x is equal to 1 and y is equal to 1. So we have the same input. Therefore, our output will be 0. And the opposite of XOR is we have the XNOR. So for XNOR, so it's just the opposite of XOR. So if our inputs are the same, so we will have an output of 1. And if our inputs are different, our output will be 0. For example, we have here x is equal to 0 and y is equal to 0. So we have 0 x nor 0 is equal to 1. And we have here 0 x nor 1. So they are different. So we have a 0 as our output. And let's say we have 1, 0. So different input. So 1 x nor 0 is 0. And we have 1 x nor 1. So we have the same input, which is both of them are 1. So therefore, our output for x nor is equal to 1. And we have different graphical symbols, okay, for our logic gates. So the graphic symbols are abstraction of the physical component that produce the equivalent logic 0 or logic 1 as an output signal. So if input logic requires are satisfied, so for example, we have here, so this is the symbol for AND gate, and we have here two inputs. We have X and Y and Z to be our output. Again, an absence of an operator, or let's say they have used dot, meaning that that is an AND operator. So this is our symbol for OR gate. So we have input X and we have input Y. So let me correct this one. So this should be X plus Y. So Z, okay, this should be equal to X plus Y. There. Okay, so we have X plus Y. So this is the correct one. So for NOT gate, okay, so let's erase this one first. Okay, so we'll not be using. So it should be x plus y. So going back, so we have the NOT gate. So it's just the complement. So we have our input x, okay, and our output would be x prime, the complement of x. And this is the symbol used. Okay, and then we have here the XOR gate. So this is our symbol for XOR gate. Okay, so it's just like an OR gate with a line behind, right? So we have the input X and Y, and our output would be Z. So if you can see, this will be our operator used for XOR. So it is read as Z is equal to X XOR Y. And we have here a NAND gate. Okay, so this is the symbol for NAND gate. So it's the same as the AND gate. And the difference is it has a bubble on its output. So the bubble on the output denotes that the output is complemented, or we will get the complement of the output. So we have here X and Y, and we are going to complement. And we have here the NOR gate. Again, it's the same as the AND gate. It is the same as the OR gate. The difference with its symbol is it has a bubble on its output. Again, it denotes that that it will get the complement of an OR gate. And we have here the buffer gate. So we have an input X. Okay, so whatever your input is, it is also your output. So what is a buffer? Okay, so the buffer, it simply copies the input to the output from the logical point of view. So a buffer is no different from a wire. So it might seem useless. However, the analog point of view, the buffer might have a desirable characteristic such as the ability to deliver large amount of current to a motor, or ability to quickly send its output to many gates. Okay, and for the XNOR gate, so it performs, okay, the inverse of an XOR. Diba? So again, there is now a bubble. If you can see, we have a bubble here. So we have here an XOR gate, the same as symbol as XOR gate, and the difference, it has a bubble on its output. Again, the bubble indicates the okay, so next, okay, so let us look at a combinational circuit. So a combinational circuit are made of one or more logic gates. What is perhaps noteworthy about combinational circuits is that the output is immediately produced when input values change. To arrive at the final output of the logic circuit, we must first consider the inputs at every logic gate and evaluate the individual outputs until we arrive at the gate that will determine the value of the final output. Okay, and combinational circuits requires analysis of individual gates, input and output, until final gate that will determine the output of the entire circuit. And we use the truth table. Okay, our truth table is useful for tracing the signal from the input to the output. Again, okay, so we have the formula 2 raised to n, okay, to get the possible combinations of input values, where n is the number of input. So we have here an example. So let's say we have here the function is equal to x or y and z. So again, our combinational circuit or our logic circuits, okay, can be represented in three ways. Okay, so it could be represented as a Boolean function, expression, or it could be represented by logic symbols, logic gate symbols, okay, our combinational circuit, or it could be represented by a truth table. So let's start with the truth table. If we are going to observe the number of inputs, we have X, Y, and Z. So these are our inputs. So we have three inputs, namely X, Y, and Z. Using the formula 2 raised to n, wherein n is the number of input, so we have how many inputs? We have three inputs. We have X, Y, and Z. So 2 raised to 3, okay, 2 raised to 3 is equal to 8. So therefore, we have 8 possible combinations. And how do we plot, okay, our 8 possible combination? First, okay, you have to write, so since we have 8, so 8 divided by 2, that's 4. So therefore, the first 4, we always start with 0. So we have 4 zeros, so 1, 2, 3, 4, followed by 4 ones. There. So that's how we write the first input. Okay? And then, since we have 4 here, so we will again get the half. So it will become 2 zeros. So we have 0, 0, followed by 1, 1, 0, 0, 1, 1. And we have here for the last input, so we have 0, 1, 0, 1, 0, 1, 0, 1. Okay, so this is very useful. Later on, we'll be discussing more of this, okay, in our topics on min terms and max terms. Okay, so it is very important, okay, to know how our input are arranged on our truth table. Okay, so given our input, so the last column will be our output. So we are going to substitute the variables on our given expression, that is X or Y, and then we have Z. So it follows the same priority. So it always start or prioritizes anything inside the parentheses. So we'll do OR gate first, or we'll do OR operation followed by an AND operation. So for example, we have here 0, 0, 0. So let's say the value of X is 0. X or 0 is 0. And then the output is 0. 0 and 0 is 0. So let's say we have this one, 0, 0, 1. So X or 0 is 0. So 0 and 1 is 0. Another example, let's say we have here 0 or 1 is 1. 1 and 0 is 0. And how about this? Let's say we have here X or 1 is 1. 1 and 1 is equal to 1. So we have 1 here. There. Okay, and as for our combinational circuit, okay, we can actually substitute all this possible combination with X and Y and process it or evaluate on each gate. So for example, let's say let's select 1, 0, 1, X is 1, Y is 0, and Z is 1. So let's say X is 1, Y is 0. So 1 or 0 is 1, right? So we'll place 1 here. Diba? So let's say the value of x is 1. The value of y is 0. So 1 or 0 is 1. Okay, let's say the value of z is 1. So we have here 1 and 1 is equal to 1. So we have 1 as an our output. And that's all for our presentation. So do you have any questions? You may raise your hand on our, Okay, if you have mic, you raise your hand. And if you don't have any mic, feel free to write your questions on our chat box.